Right guys, introduction to assignment 1, and some of you are last year's students who are all familiar with layout of assignments, some of you are new. I'll give you a paper copy of the assignment once, and then if you lose that or want another copy, you can get it off the website where you hand in, and I'll show you that after we had a short break. I was halfway through putting the assignment up there this morning and then realised I needed to see Jack and Robbie for their tutorial, so it's halfway through being done. I'll get that on there and I'll show you where that is immediately after we have a short break mid-session, or a convenient point. So it's got I'll get wrong because it's got University Campus Suffolk, and that should have University of Suffolk on it. I'll sort that out too. PLCs, assignment 1, it's a technical assistance report on design, architecture, operation, interfacing and communications. Okay, you've got a guided word limit up to 2,500 for this assignment, and that's due in 4 weeks' time on Wednesday, the 2nd of November 2016. Okay, so that's where we are with that, and I hope that 2nd of November is Wednesday. Yes, it is, and that will be at 23:59 on that day as well, and you do get the remaining 59 seconds as well should you need them. Alright, if you're handing after that, unless you've agreed in advance an extension to that, which you can do via the electronic My Suffolk system and Oasis, you'll have to provide formal evidence, and you may have it refused, so best not to rely on it. Okay, but you get a stand. You can, for this assignment, you may be able to get, if you've got the right evidence, and that's a doctor's note or a formal letter from employers or something saying you've had difficulty, you might get a 2-week extension. The second assignment's a bit more difficult because that's getting close to board, so you'd probably be looking at applying for a deferral there, where you defer the result until the summer board. Again, you'd need to provide significant evidence of why you're having difficulty. You've got 4 weeks. 2 weeks from today, I'm putting a second hand-in point up for a draft hand-in, and again, so Wednesday in 2 weeks' time, whatever that date is, you can hand in a draft, and within a week get some comments back from me so you can improve on the work. Okay? So, this assignment 1 is worth, I believe, 40% of the overall mark for the module, and it covers learning outcomes 1 and 2. So explain design, architecture and operational characteristics of PLCs and their interface to systems they control, and explain PC to PLC and PLC to PLC communication techniques, the use of HMI and SCADA software, field bus systems and their applications. So that's what this assignment covers, and I know we haven't covered some of that yet. We're going to do a bit more today, and then I'm going to top that off next week. Okay, although the bit about communication techniques and field bus is going to be quite thin from me, but a significant research area for yourselves. Okay, so that's going to be left a little bit open. I'm going to touch on the water of that and then let you loose to do some research around that area. Okay, and you'll see that when I show you a bit further down in the document. Can you make sure that you hand in, some people still persist in turning their Word document into a PDF and handing it in as a PDF. I put my documents up as PDF so that they can't be changed. Please hand your work in as a Word document. It's much easier for us to comment on a Word document than it is on a PDF. We can use the commenting facility a lot easier. With a PDF, I have to try and find some white space to put a text box somewhere on your page. Okay? I am very strict on navigation around your document. Okay? I want to see you, if you're referring to a section earlier or later in your report, I'd like you to tell me what page number it's on. And I should be able to click the little page number thing and type in the page, and it goes to that page. I want to see you properly title all diagrams, figures, pictures, tables, and refer to them in your text. If they're not referred to, they're not there for a reason. Tell me within your text what figure 1, figure 2, figure 3, what benefit that is. Use it. If it isn't being used in your text, that's there for no particular reason other than to adorn the page with a pretty picture. And that's not what we're about at this level on this type of report. Okay? So they should be properly numbered, and you're going to be, if you haven't already, you're going to be taught by Adrian about the referencing system that you should be using to your background reading, which is the Harvard referencing system. And I can also provide some guidance on that as well. On this page here, which you can't see on the screen really very well, but you've got in your assignment, is your guide to how you can achieve each grade in each of the kind of areas I'm looking for you to do or perform in this particular assignment. So down the left-hand column are the things I'm kind of asking you, the areas I'm asking you to do work in. Evaluate the design and architecture, operational characteristics of PLC. Analyze the ways in which PLCs interface with the systems they control. Analyze 4 communication standards used for interfacing PLCs. Evaluate SCADA and HMI. So they're the key kind of technical details that's going in this report. Then we look at field bus systems, technologies, and explain advantages, compare and contrast 2 different ones. So that's where you're going to be doing your kind of research here. And then we look at some couple of general things. The quality of your background reading. Have you referenced and read a bit? How widely have you read around the topic to actually write your report? And lastly, overall report presentation and referencing. So that's where your grade in that area will go down if you don't properly title all your figures, tables and such like, and your English and grammar is poor, or your document doesn't flow very well and I can't find my way around it. Okay, there's nothing more annoying than being told that something's in Appendix 3 and you can't bloody find Appendix 3 because I haven't been directed to the right page. So you're searching through the document instead of being able to navigate it properly. Okay, so there's marks associated for all of that. And then going across the page, it gives you an indication of what mark you'll get according to your performance in each of those areas. I don't plan to go through all of it, but you guys should be reading it to see the kind of thing that you need to do. And if we look at the top line, evaluate the design, architecture and operational characteristics. Distinction. All the technical aspects of PLC architecture and operation are evaluated and explained to an outstanding level. I like to think of merit, and it usually says excellent level in merit, as the student has done everything in that area I would have expected them to do in light of the level of this course and what's been taught. If you're going to be outstanding, you've kind of done something a little bit extra, you've gone that extra mile, you're going to be in the distinction area. That's kind of the way I think about it when I'm marking. Oh, I wouldn't have expected them to have covered that. That is really good work. That's distinction level work. Okay? In the merit, all the technical aspects of PLC architecture and operation are evaluated and explained to an excellent level. In the pass, majority of the technical aspects, so the important bits have been covered, okay, evaluated and explained to a very good level, but some aspects may contain ambiguity or lack detail. So then your work is going to filter down towards the pass area percentage-wise. Marginal fail, some technical aspects of PLC architecture are explained to a good level, but report lacks evaluation and or detail in some key areas. You've got to cover all the key things, otherwise you're going to get a marginal fail. And then the fail bit is technical aspects have not been explained, or there's a significant lack of detail across large parts of the explanation. So you can see how, as bits and pieces in your report become missing or not evident, your marks are going to go down. And the idea of the matrix is to show you what you need to do in each area to get any one of the grades. Okay? So I don't propose to go through that in detail, but it's something that you should be looking at to make sure that you cover everything. So, moving on. There is a quite lengthy introduction, but what the introduction says is that you're required to produce a technical assistance report for a manager around whether the company should adopt the use of PLCs, and they've got some old technology, food processing and packaging, relay controlled. And this manager's got a little bit of kind of outdated electrical knowledge, but don't really know anything about PLCs other than what he or she has read. Yeah? So they're looking for you to fill in some gaps around PLCs and how they work and how they interface with the outside world and so on. So with a view to deciding whether you should go down the route of experimenting by replacing their old systems with PLC units. Okay? So to help with his or her preparation of a report, I want some details. So part A is design and architecture. There you're being asked to go through the kind of three general different types of PLC, explaining how they work together, what options there are available, the design features of them, okay, and relative advantages and disadvantages of the three types. Relevant advantages and disadvantages is an important point. When you're going to be analytical about anything, that's no good just looking at the advantages. You have to create a balanced argument, and everything, no matter how advantageous it look, will be disadvantaged. There'll be something that is less than something else could offer, but you're weighing up against what you're looking for. And what might be really advantageous in one application is completely irrelevant in a different application. So it's specific. So when you're arguing a point, and that should go all the way through the degree, try and be balanced in your argument and in your decisions by saying not just what the good things are, or just what the bad things are. It should be, your argument should be balanced, and you must consider both sides of the argument. And then towards the end of that, you're asked to go through what the PLC scan situation is and what its implications are. So we kind of covered that in class, and we've also talked about a little bit about the three different general areas of PLC, the little brick ones, the modular, and the rack mounted. Okay. Part B, interfacing with the PLC with the systems they control. What they're asking for there is the methods used to interface the PLC with the following input types: mechanically operated limit switches for sensing machine movement, electronic type optical, inductive and capacitive sensors, and analog inputs, which I'm going to go through a little bit today. Certainly the analog inputs, I'm covering that in today's session. Furthermore, I understand that PLCs can have both relay and transistor type outputs. Please explain the difference between these two types with a summary of the advantages and disadvantages of each. And I have briefly covered those in class as well. Yep. Part C, PLC communication standards. Believe industrial automation systems communicate using serial communication links, but there can be some confusion between the different types and data communicated using that link. I believe that most common data standards are RS-422, 485 and USB. Can you please create a table which summarizes the key performance data for these standards? The table should include an explanation of the terms used to compare the standards, which might include things like mode of operation, is it single-ended or differential, and you would need to explain what serial, single-ended and differential meant. Okay, that would be important, because this person doesn't understand that terminology. So any PLC communication specific terminology should be briefly explained to someone that you think, in a way that you think they'd know, someone who knows nothing about this area of engineering could understand. So in layman's terms, not lots of technical detail dragged off the internet. Maximum allowable cable length, maximum data rate and what affects that data rate. Okay, and then part D, information display and operator interface. Read about ways in which system can be information can be displayed and operator or management system interfaces can be provided. So getting information out about how much production there is, how many rejects there's been, for instance, how fast the machine is running, as well as the operator being able to speed it up, slow it down, change temperatures, do that type of thing. So it's around SCADA and HMI systems and the kind of differences between them, and I will touch on that a little bit next week. But like I say, these last two areas are where I'm going to expect you to do a bit of research. Okay. On the outside, they both appear to do exactly the same thing, but they are in fact quite different. Okay. And then lastly, the last little bit, field bus networks. Understand that field bus technology has a range of uses in industry. Please provide a summary of what field bus technology is, and using two typical example uses, explain briefly what the field bus does and how it works. Okay, so there again, that's going to be an area of research for you towards the end of the report. Okay, so has anybody got any questions? There are some general things to comply with. Should be between 2,200 and 2,500 words in length, excluding the contents page and any additional detail included in the appendix. Okay? Should not be analysis in any appendices, just additional information. Okay? If it's important to the report, it goes in the main body. Words in tables and figures don't count. That doesn't mean you put everything in a table, so all your extra words in the table, because I'll spot that a mile off. Okay. Your report should be presented in Times New Roman or Arial with a point size of 12 and 1.5 line space, and that kind of gives you, it makes it look nice and it gives some white space to be able, for your marker to be able to comment in. I mark electronically, but some people still like to write on the page, so it gives them room to do that. Okay. Make sure it includes the front page, contents page, and number it. Diagrams or tables are numbered and labelled, and your name is included in the page footer. Okay, please reference to the Harvard referencing system. Okay? Yeah? Any questions? Marcus? So, in terms of actual PLCs this week, what we're going to do, take a look at digital and analog input and output devices and signal types, so you now know where that's relevant to the assignment. We're going to look at how PLCs process analog signals, or the basics of it. I'm not going to go into huge detail, right? And then hopefully we can get to there before break, and then after break we're going to be looking at how we document PLC programs, and I know some of you already started to look at that last week, and those that have already done PLC, certainly with me, will have at least done it even if they can't remember how to do it. Hey, Jordan? All right? But, you know, so we'll go through that again, and then I'm going to go through the introduction to the first what we call real program that you're going to write, which is a pedestrian crossing traffic lights. So I'll give you a good start on that one by going through some techniques to do it, and then the idea is you carry that on and finish the program off to the end. All right? So that's the plan anyway. So, digital input device states. Oh, we want a handout. Right, so digital devices. What digital means is, but by their very nature, like a digital signal can only have two states in its most basic form. It's either off or it's on. So digital inputs can only be in one or two states, off or on. Yeah, an old way of saying that in logic terms is logic 0 and logic 1. Yeah. But whatever term you use, it can only be off or on. Nominally, with PLCs, the off state is represented by 0 volts and the on state represented by 24 volts. However, like anything else in life, things have tolerances. So can't guarantee exactly 24 volts every time, can't guarantee exactly 0 volts. So what they have to do is have things between a certain specification. So they might have anything between, on the PLC input specification, anything between 24 volts and 21 volts is considered to be on. If you supply that with 21 volts or above, you're guaranteed to turn the input on. And anything below 3 volts, and you're guaranteed for it to be off. And you should not have your device be anywhere between the two because it's unsure. You consider that as being unsure what that would do. Could be off, could be on. So if you're making a sensor for PLC input, or you're choosing one, it has to have an on that is greater than 21 volts, between 21 and 24, between 21.1 say and 24 volts. Then you'll guarantee that it's going to turn that input on. And it has to have an off voltage less than 3 volts. And then you'll guarantee that if you feed that into that input, it's going to work. Do you understand that? Yeah? This device is going to output voltages between off that is less than 3 volts, on is greater than 21 volts. And then that will work with that PLC input. If it's got any other specifications outside those, then you're going to have problems. Okay. Now, with a mechanical switch, if you supply, let's just put another page in here. If you supply a mechanical switch, let's say a limit switch, it's a normally open limit switch with a wheel actuator, say, right? And this is your 24 volt supply from your PLC, and then you take that down to the PLC input X1. Yeah. With that, and 0 volts is somewhere on the PLC as well, so 0 volts. That creates through your programmer circuit. All right, you're guaranteed to put 24 volts on there as long as your supply lines is 21 volts or above. You're okay. It's the electronic sensors you've got to be careful to specify the correct levels. So they'd have to manufacture, if they know generally PLC logic 1 is above 21 volts, they've got to manufacture sensors that are 21.5 volts when they're turned on at least, and then I'll work with those systems. Okay. Other than that, digital inputs are fairly simple in terms of the way that they work. On or off, they can be switches, they can be a range of different sensors, which we're going to look at in a minute. So, digital input devices, mechanical switches, push buttons, reed switches, etc. Okay. Advantage, one of them, typically. Any ideas? Yeah, okay, relatively cheap. Yeah. Easy to replace. One of the key ones is handle variety of voltages. Key disadvantage? Disadvantages? Well done, Marcus. Mechanical life. And have to make contact. They physically make contact with the object. So if you wanted to count lightweight bottles moving along a conveyor, it's no good putting a limit switch in front of them because it's going to knock them over because it's making contact with them. For instance, just one example. Okay, you might, through your research, you might be able to find, if you're looking at mechanical switches, you might be able to find other advantages and disadvantages, but that's just a flavour. Capacitive proximity sensors. Okay, what these can do is sense the presence of metallic and non-metallic objects. So there's like they use a capacitive effect to do that. Non-contact. So as opposed to those, they don't have contact. Something just passes in front of them. Okay. Disadvantages? Yeah. I'm going to put sometimes tricky to set up in a consistent way. Things can interfere with them. More expensive. Well, relatively they are. Fixed voltage. Some of them have a variable range, so you've got an adjustment on them, so you can set how close something has to be to them to make them go off. Yeah. No moving parts, which is probably they haven't got a mechanical life. In other words, they might go down electronically, but mechanical life, they ain't no contacts to burn out, and there is no mechanical actuator to get broken or wear. Well, they can drift, so if there is an adjustment on them, there are cases where you might have to adjust that adjustment occasionally, but I find them, unless they're usually pretty consistent. But generally they're quite close proximity devices. They don't work like 10 meters away or anything like that, or even a meter. You're talking about sort of 4 or 5 centimeter distances at most, Marcus. Oh yeah, that you could. Yes, you can. Some do. Some you buy, whether you want dark on or covered on or covered off. Some have it selectable. So whether what you're saying is it turned on when you cover it, or is it turned off when you cover it? Some of them are selectable. Some of it you do it by the way you wire it. So they give you 4 wires and you choose which output you're going to use. Just depends on manufacturer and style. And there's thousands of different ones out there. All right, and that's true of all these electronic ones. You've got not only the NP thing to sort, but you also got, do you want it effectively normally open or normally closed, as you're saying, covered on or uncovered on. Yeah. Many of them are selectable these days. All right. Digital input devices further. Inductive proximity sensors. Okay. Similar advantages and disadvantages. To the capacitive type. So I'm not going to write them all out again. However, the inductive proximity sensor will sense the presence of a metallic object only. So you can kind of use capacitive and inductive in combination to sort plastic and metal objects. And I'm not saying it's a metal detector. It isn't that good, but it does only sense metal objects. So on our conveyor system, there is in one position there's an inductive sensor and a capacitive one. So the capacitive one says there's an object there, and the inductive one says whether it's metal or not. So if the metal one's on and the inductive one's on, it must be a metal object there. But if the capacitive one's on and not the inductive one, that must be a plastic object. So you can put them in different bins. Okay? So that will allow you to the combination of those two can give you discrimination between metal and plastic objects. Okay? So that's, in a similar way, they work in quite close proximity. They're not something that's going to work over even like half a meter. Metals and other materials. I'm not sure how well any of them will sense wood, if I'm honest. I've never tried it. I've not come across any machines made of wood, but there might be some out there. I'm not knocking your idea, your question down. Yeah. Oh yeah, and they sense them. Yeah, like these photoelectric ones. Yeah. Well, because they're using onto photoelectric 3 general types: diffuse, which is the one with the top diagram. You'll probably see it better in your notes, where you're actually reflecting off the object. So in the unit, there's a transmitter and a receiver. The transmitter sends out a light signal, and that reflects back off the object to the receiver, and that can be light on or dark on again, Marcus. So, you know, either when the object is in front it's on, or when the object is in front it goes off, and they're more likely to be selectable on this type of sensor as well. Okay, these will work over a much bigger range. I've had them work over distances of at least 2 of these tables reliably, the reflector type. Okay, so they're certainly not like your light guard accuracy, and not that reliable over that distance, but they will, like you can do these over distance. Second type, retroreflective. This is where you have a special reflector on the wall and your sensor here, and the light is reflected back from that reflector, and when something goes in front of it, it breaks that reflection. So the object coming between the transmitter and the sensor with the receiver in it stops the reflection and either turns the circuit on or off again. And then the last type is where you have a separate transmitter and receiver, one position, one some distance away, and the transmitter transmits to the receiver and you block it and sense. And those ones are the ones most likely to work over a longer distance. The issue with them is getting the two sensors lined up and making sure they stay aligned. But you can do that over some quite considerable distance. Have no idea, Lewis, but probably. Is that might be a light curtain. So you can have walk-in machines where they're kind of completely open, but they're guarded by a light curtain. So as soon as you put your hand in, any of the lights being broken. But they're for obvious reasons a lot more sophisticated than what we're talking about here, sensing just machine movements, but would work on some kind of similar principle. But as you can imagine, that's about someone not putting their hands in the guillotine. That's going to be a little bit more important than just making sure a piece of machinery is in a certain position. All right? Yeah. Again, they got kind of some similar advantages and disadvantages to the other two, but their big advantage over them is the distance apart, that you can have the transmitter and the receiver and still sense objects. But again, they're non-contact. They are quite expensive compared to mechanical. So, you know, that's about weighing up what your needs are. And there are sensors out there now that'll sense different colours and do all sorts of things that you didn't used to be able to do. It's a minefield, really, trying to pick a suitable sensor in some cases. Well, when you say accurate, what do you more reliable or? Yeah, because accuracy, I don't know. That's a difficult thing to define, accuracy. Because if I put two gauges here and one was digital and one was analog, which would you say is more accurate? Sorry? I'd say you don't know enough to decide. Because accuracy is not about how fine the divisions are, and most people would say digital must be more accurate because that's digital, but that ain't what accuracy is about. It's about how close to, if you know a pressure signal's 20 psi, accuracy is about how close your measuring device is likely to be to 20 psi when you measure it. And that's not the same as what the resolution is that can measure down to 0.1, or the other device can measure to 1 psi. It's got nothing to do with accuracy. So they're difficult terms to define. I don't quite know what you mean by accuracy in terms of these. How reliable, how consistent they are in detecting something, yeah, will be often depend on how well they're set up. All right? Okay, analog inputs. Consider a case where you want to monitor the level of water in a tank. Yep. We could put level switches at different heights to provide discrete levels. empty, half full, full. We could put quarter full, 3/4 full. We could put any number of sensors in there we wanted if we wanted to sense every meter in a big tank if we wanted to. Yeah. But what that would do is use an input for every level that we wanted to know, and it still wouldn't give us actual information about, or accurate information about the level in that tank. It'd only give us information in steps. Okay. If we put an analog sensor into the same tank, so I'm not going to go into details, but what that's likely to be is a pressure sensor, because the pressure, as you probably all ought to know, the pressure at the bottom of a tank is dependent upon the head of water above it, how high the water is. Doesn't make any difference what the dimensions of the tank are, lengthwise and widthwise. The pressure in the bottom is dependent upon the height of the water in the tank. Yeah, so you'd have some kind of pressure sensor that would give you typically a 0 to 10 volt signal, or a 4 to 20 milliamp signal, for instance, and that would give you those signals 0 when that's at the bottom, say, and 10 volts when it's at the top. But any distance in between, so halfway, would give you 5 volts. 25% full would give you 2.5 volts, and so on. So this signal from here, one fallacy is that people say analog signals are constantly changing. No, they're not. But they can be any value between two limits. They might well be going up and down like that and changing at some points, but at other times, if the water level's not changing in that tank, the analog signal won't be changing. So they aren't constantly varying, but they can be any value between their two limits, in this case 0 and 10 volts or 4 and 20 milliamps. Another kind of aside is 4 to 20 milliamps is commonly used. Does anyone know why? Why 4 to 20 and not 0 to 20? If you use current, you're talking about using a loop through various devices. If you get 0 milliamps, what that means is you've got a break in that circuit. You've got no current flowing. You've got a fault. Because you've got a positive, you effectively got a positive 0 on that signal. If you get actual 0, you know somebody's opened the circuit and took a wire out, or a wire's fell out of a terminal somewhere. It's not really that important for this module, but I thought I'd just cover why you generally start current signals 4 to 20, and a common signal used in instrumentation is 4 to 20 milliamp. Okay. I think the Mitsubishi PLC analog inputs, you can choose either 0 to 5 or 0 to 10 volts, or you can use 4 to 20 milliamp. So, what the PLC, how does the PLC handle this voltage between 0 and 10 volts? Or for ease of explanation, I'll choose to talk about 0 to 15 volts, and the reason for that will become obvious in a minute. PLC can internally, as far as the processor is concerned, can only handle digital signals and numbers represented digitally in binary form. So any computer that I know of only understands two things, off and on. But it can deal with those offs and ons really quickly, and it can combine lots of offs and ons together to understand more complex information. That's really what it's doing here. To handle analog signals, a separate analog input module is needed, so you have to buy another module for your PLC. Okay. Inside that module, for inputs, there'll be something called an analog to digital converter. What that does is it converts that 0 to 15 volt signal into a binary number that the PLC can understand and process. So, if, for example, our input used a 4-bit binary number, so that's a binary number that's got 4 places in it, I'll write it here. This one represents the units, that one represents 2, that represents 4, that represents 8. If we add all them up, it makes 16 different combinations. Yeah, we could have it from all off to all on. It's 8, 12, 13, 14, 15, plus all off, 15 different combinations we can record with 4 bits. So you have 0 volts represented by binary nothing, 15 volts represented by binary 1, 1, 1, 1, that's 8, 12, 14, and 1 is 15. 7 is represented by them all being 1 and that one being off. 4, 5, 6, 7. So each volt in that 0 to 15 is represented by a binary number between 0, 0, 0, 0 and 1, 1, 1, 1. Yeah? However, what that means is it's like having 15 sensors at 15 different levels in that tank. We're still only measuring in steps, but they're 1 volt steps in a 0 to 15 volt signal. The error created because you're not going to hit signal 1 until you get to a volt. So there's an error, as that step error has got a name, it's called a quantization error. So any analog to digital processing will involve some kind of quantization error. So it's about how do we reduce that. How do you think we reduce that? 4-bit binary word represents 2 to the power 4, 16 different voltage levels. So that's from 0 to 15. How do you think they get round that problem? Real analog input specifications. Dependent upon manufacturer and PLC model, an analog input might use, for example, a 12-bit word that represents 2 to the power 12 different combinations, or approximately 4,000 steps for that voltage. So in our example, that would mean our 15 volt signal would be represented in 3.75 millivolt steps. So the quantization error is 3.75 millivolts now, as opposed to a whole volt. So we can represent that level from empty to closed in that tank to a resolution of 4,000 steps if we use 12-bit word in our A to D converter. If we use a 16-bit word, 2 to the 16 is approximately 64,000 different steps, meaning our 15 volt signal will be represented in 230 microvolt steps. So a quantization error has gone right down to a really small amount. But it still is a step. It still is a small error. But in most applications, that would be sufficient for it to work well enough. Yeah, the more bits you use in that binary word, the more different combinations you can have of ones and noughts. Yeah, so it's about what powers of 2, and that's 64,000, and that's actually 65,000 and something for a 16-bit word. Well, all I've done there is gone 15 over 64,000. And that's approximate, because actually that's 65,000 and something. If you do 2 to the power 16 on your calculator, you'll see what it is. That's what they call 64-bit processing when they talk about your processing. Yeah. So if you've got a 64-bit processor in your laptop, that can handle word size up to 2 to the power 64. But the problem is what it usually uses, use half of it for positive numbers and half of it for negative ones. So it's not quite that way. But with this, that's using all of it for a positive signal. Alright? No more detail than that is needed. Just that you understand that that's doing a conversion and it's converted into digital form. Analog outputs, okay, for instance, you might have a motor controller, a motor speed controller that requires a 0 to 10 volt input to vary the speed between 0 and 2000 RPM. In that case, the PLC would have the desired speed as a digital number, let's say a 12-bit digital number, right, with all ones being full speed, all zeros being no speed, and then all the other combinations in between, to create using a digital to analog converter, so the opposite in the output, to convert that digital number into a voltage between 0 and 10 volts at the terminals. So it's kind of like the input device turned the other way round. And on the FX, you can buy analog boards that have got, say, 2 analog inputs and 1 analog output on, depending on what you can buy ones that are just in and just out as well. So there's a number of combinations, and you have more flexibility than that with your kind of rack mounted. So you'd need a special output module with a D to A converter to convert the binary number into the required voltage output between 0 and 10 volts, or indeed 420 milliamps. So it's just kind of the reverse process. And again, there's going to be a quantization error in that output signal. It's going to have a step to it, although if you looked at it on a meter, you probably wouldn't be able to see it. Okay?